Let's briefly discuss the mathematics of uniform motion. For uniform motion, the plot of the object's position versus time is a diagonal line. The average velocity, which is defined to be delta x over delta t, is equivalent to the slope of the position versus time curve for uniform motion. Here you can see it very easily. Slope is defined to be rise over run. In this case, the rise is delta x and the run is delta t. So V average is literally the slope of this uniform motion constant velocity line. For a straight diagonal line, this slope is the same everywhere along the line and is independent to the time interval we examine. That is, the ratio of delta x over delta t is the same for any delta t that we examine. And there's no distinction between an average velocity and an instantaneous velocity for objects with a constant velocity. Note, by simple rearrangement of V average equals delta x over delta t, I can solve for delta x. It's obviously delta x is equal to V average times delta t. Here it is, delta x rearranged is equal to V average times delta t. Now this V average times delta t being equal to the displacement delta x has a beautiful geometric picture that goes along with it. Here, on a velocity versus time graph, we have the velocity for uniform motion being a horizontal line indicating the uniform motion, the constant velocity. So we have this horizontal line, and if you look at V average, what that is, it's the height above zero of this line, and delta t is the width of the line segment we're considering. If you look at V average times delta t, it's clearly the area of this gray rectangle. V average times delta t is this rectangular area. And so delta x being equal to V average times delta t is the same as the area under the velocity curve from t naught to t final, since that area is just the area of this rectangle, V average times delta t. So that's one very important thing to note, that the displacement is equal to the area under the velocity versus time curve. This turns out to generalize. Another thing to note is that if we expand delta x into x final minus x naught, we can rewrite this as x final minus x naught is equal to V average times delta t, and we can solve this for x final. So x final is equal to x naught plus V average delta t. Or if you like to think of it, it's x naught plus delta x if you think about it. So we have this equation, x final equals x naught plus V average times delta t, which is useful for situations where you have uniform motion in one dimension.